This is a recording to show how to build magnetic balance in interactive physics. First, I'm going to take this rectangle, and this will be the pivot, and I'm going to do a couple of things with it. One is I'm going to anchor it down because gravity needs to be turned on here to make the balance work, and therefore if I don't anchor it down it would just fall down. So the other thing I'm going to do is I hit Control I. I set its charge to 0, and I make sure that its x distance is at exactly 0.300, and I'm going to also shift it up. Okay, that was too far. Okay, even further down. I think I'll do that manually. There, that's where I want it, I think, right here. There we go. That's good. If I could grab the anchor now. There we go. Alright. Then I make a second bar here. This will be 6 units long, which in this case here would be 60 centimeters with the scale. I'm gonna hit again Control I, put its charge to 0. I hit Control J and change its color to gray. And now I'm going to put it on top of this pivot point here. There we go. And now I'm going to double check that its distance, its middle is at exactly 0.300. There we go. And that's where I'm going to join the two. This pin joint here is what I'm going to use. There we go. Okay, if I hit run now, well, the whole thing was totally balanced to begin with, so obviously nothing is happening here. Okay, reset. Okay, now I'm going to zoom in, and I'm going to make a magnetic pole here. There, that's the size I want. Again, Control I. I'm going to change this to -1 times 10 to -5. I'm going to change its appearance with Control J to red, and I call it north, and I show the name. There we go. Now I copy this one, Control C and Control V. There we go. I forgot to actually copy this one here as well. So Control C and Control V. There we go. And now I copy this one again, Control C and Control V, because now I need a couple of south poles. So I change the appearance to this blue here, call it S for south, and I change this one here to a positive 10 to -5. Okay, and then again copy and paste it, Control C, Control V. Okay, I'm going to put this one right there and connect it with a rigid joint so that this one is not rotating on me. Now I'm going to grab this one here and put it over there, also with a rigid joint. Gonna grab this one here and do the same thing, of course. Oh, I have to be careful because, well, I want to put the north here on the left. On the other one, I want to put it on the right hand side. Oh, this might have been off the screen. I apologize when I did that earlier. One moment. There. This is what I did earlier with the south. Again, the rigid joint here. Now I'm going to do this one here with the north. Rigid joint. Now going back here. South. Rigid joint. Okay, now I'm going to zoom out. Oops, and then I somehow lost it for a moment. There we go. There they are. Push this up a little bit. And now I'm going to put this one here. And now I could measure a distance of 20 centimeters and determine the magnetic force for that. And then I notice that I'm not done. I have to anchor this one down. There we go. And then wherever I shift it to, the anchor will come along and it's just going to stay there. This one is the only flexible piece, the one here with these two poles, so that would rotate. If I turn the run button on, and it's pretty fast here, just to show you, I'm going to change this one here, and it's still pretty fast. For that I need a counterweight, so I'm going to make yet another rectangle here, and I don't want to set it at the exact end, so I want to set it at this point here at 2/3 out, so it doesn't produce a torque on the end, but it produces a torque here at 2/3 out. Again, I'm going to hit Control I, and I set this one here to its charge to 0, and then I would have to see how much mass I need. So for example, 5 kilograms. I already got an idea here how much I need. Okay, and then I need another rigid joint to connect this one here. There we go. And if I hit run now, then apparently I took too much because it's pivoting down on the right hand side, so I try something else. Control I here, 3.5 kilograms, and that's pretty close. I try one more, 3.2 kilograms. Again, Control I, 3.2 kilograms, and now you see it pivots in the other direction, so the correct mass would have to be between 3.2 and 3.5 kilograms for a distance of 20 centimeters. And then hit reset, and then go to another distance, 10 centimeters, 30 centimeters, 40 centimeters, and so on. These calculations will give you an idea of how much mass you should put on there and how much the force is. So, I just noticed something here, that this one here, right there, should be really on the line so that the two poles are on top of each other. I think I arbitrarily shifted earlier when I was done. Okay, anyway, so here are the calculations. Coulomb's law, 8.99, 10 to the negative 9. Then I have I'm sorry, that's not negative 9, that's just 10 to the 9th times, then I have 2 equal charges of 10 to the negative 5, negative 10 to the negative 5, so I square these, and then I'm just going to do 1.0 meters squared and go off that, and yep, that should work. Okay, there we go. So at 1.000 meters, I would have a force of 0.899 newtons. That's how much these two poles would be repelling. Now, the counterweight over here, or a counter mass, I would have to take the force, divide by 9.8, because that will give me the mass. And then I realize that this one is only 2/3 of the way out. So its lever arm is only 2/3 of the total length, while here, of course, the pole is at 3/3, so the entire length out. So I'm going to multiply this, as the lever arm here is 2/3, I'm going to multiply this one here with 3/2, because for the fraction for the lever arm, I need to use the reciprocal for the force to act at that point. Okay, so multiply by 3/2, enter, and so at 1 meter distance between the two poles, so if I push this one here up to 1 meter, I would get a force of 0.899 newtons, and that would be counteracted by 137 grams, or 0.137 kilograms. This here will give you an idea of how much mass you have to put on. Now, for example, 0.137, let's take one more, 6 there, for a distance of 20 centimeters, so 0.2 meters, the one I used earlier when I built it, so divide by 0.2 squared, I come up with 3.44, and you may remember that 3.5 was just a little bit too much, and 3.2 was a little bit too low, and that's why I said earlier it's between 3.2 and 3.5 kilograms. And then if you want to go on for other values, in this case here I'm just going to hit second entry because it's quicker, so just go off that 0.1376 that I calculated earlier for 1 meter, but divide that by the square of each distance, so 13.76 kilograms at 0.1 meters. So if I put the second magnet over here, or for example at 0.5 meters, 0.55 kilograms, so I would put the magnet right here. Okay, now these are benchmark figures. Notice that when you put an exact 0.550 kilograms right here, and the magnet is at a distance of 0.5 meters up here, this would be the vertical 0.5 meter distance, that the 0.550 in fact would be too much. You would have to use a little bit less, maybe in the neighborhood of 50 grams less of 0.50. That's a general rule for all of these. All of these numbers that you come up with here theoretically subtract in the neighborhood of 30 to 80 grams or so, so 0.03 to 0.08 grams, and you will see that it balances much better. And later on when you're done, you would actually have to explain why you had to subtract that. I'm not going to give that away at this point.